This lecture is about measure and conquer. Measure and conquer is a technique to upper bound the running time of a branching algorithm. We're going to look at two problems around independent sets. So the first one is about an enumeration algorithm to enumerate all maximal independent sets. And then we're going to look at an algorithm to find a largest independent set, and we analyze their running times. First of all, let's recall what a maximal independent set is. So of course, a set of vertices is an independent set if there's no edge that connects any two vertices in the set. And such an independent set is maximal if it is not a subset of any other independent set. So if we have a set of vertices that is independent and we cannot add another vertex to this set, so that we still have an independent set, then we say that this independent set is maximal. So on the left here you have an independent set with two vertices, and that is actually a maximal independent set because, well, whenever we add a vertex to the set that we obtain is not maximal anymore. And on the right hand side here we have a maximal independent set with four vertices. Okay, so the problem that we consider now is the enumeration variant, which asks us to enumerate all maximal independent sets. So the input is a graph G, and the output is all the maximal independent sets of G. So if we have this graph on four vertices here, we need to output three vertex subsets. So that's three independent sets. The first one is AD, the second one is just the vertex B, and the third one is the singleton set C.
Our algorithm will be based on the following observation. If we look at the closed neighborhood of a vertex V, so V and all its neighbors, then we observe that every maximal independent set contains at least one vertex of this closed neighborhood. So this is because that if we have an independent set that contains none of these vertices, then we could add V to this independent set. So the first independent set was not maximal. This brings us to our algorithm, where the input is graph G, and we have already constructed a partial independent set of G. So we have already put some vertices into the independent set. Now the output is all the maximal independent sets that are supersets of the set I that we are given. So if we initially call the algorithm with G and the empty set, this will then enumerate all maximal independent sets of G. Okay, so first of all, what the algorithm does is, well, it takes these vertices in I and all their neighbors and deletes them from the graph to create a new graph G prime. Now, if G prime has no vertices, then we cannot add any more vertices to the set I, so we output I. Otherwise, we select some vertex in G prime, and we select one where the degree of the vertex in G prime is minimized. So we select one where the degree is equal to the smallest degree in G prime. And so that's our vertex V. As an example, let's take a vertex V of degree 2. And now we enumerate all the independent sets that contain, well, everything in I, and one of these vertices in the closed neighborhood of V. So for every vertex U in the closed neighborhood of V, in the graph G prime, we add this vertex U to the independent set and then we make a recursive call. That's our algorithm. Let us now upper bound the running time of this algorithm. And we do this by looking at the search trees that correspond to executions of this algorithm. We will denote by L of n an upper bound on the number of leaves in any search tree of the algorithm for an instance where G prime has at most n vertices. And since we assume that L of n is exponential, we can write it as 2 to the power alpha n. So we want a good upper bound on the running time, which means that we want to minimize alpha. So we will go ahead and minimize alpha, subject to some constraints that we get from the branching algorithm. And the constraints that we have are that, so below a node, how many leaves can we have? Well, this should be at least as much as if we sum the number of leaves below each of its children. So we need that L of n is at least the number of nodes we get below its children. And so how many children do we have in our particular branching algorithm? Well, it branches on a vertex v that has some degree. And let's say that the degree is d. So then it creates one branch for every vertex in the closed neighborhood of v. So it creates d plus 1 branches. And in each one of them, it deletes basically one vertex and its neighborhood from G prime. So it deletes d plus 1 vertices in G prime because, well, every vertex has degree at least d. The vertex v that we chose had minimum degree in G prime. So we'll get d plus 1 branches, and in each of them we can upper bound the number of leaves below the children here as L of n minus d plus 1. So this should hold for every integer d that's at least 0. So we don't know what degree the algorithm is branching on, so this needs to be satisfied for each integer d that's at least 0. So now we will replace L of n by 2 to the power alpha n. And the other thing I do here is a small change of variables, so I basically set d prime is equal to d plus 1. So d prime should be at least 1. And then we will get that 2 to the power alpha n is at least d prime times 2 to the power alpha n minus d prime. And then next we are going to divide everything by 2 to the power alpha n. So then on the left hand side we get 1, and on the right hand side we get d prime times 2 to the power alpha times minus d prime. So what is nice now is that we have gotten rid of the variable n in our constraints. What is not nice is that we have an infinite number of constraints because, well, they need to be satisfied for every integer d prime that's at least 1. Okay, but we can apply now some mathematical reasoning. So let's look at one such constraint. So let's fix d prime and then look at the smallest value for alpha, and in this case I'm looking at the smallest value for 2 to the power alpha, which is equivalent, that satisfies such a constraint. And I come to the conclusion that so the smallest value for 2 to the power alpha satisfying such a constraint is d prime to the power 1 divided by d prime. Let's do a quick check. So let's say we take this constraint and we will replace 2 to the power alpha by d prime to the power 1 divided by d prime. So this is my constraint where I have done this replacement. Now I can simplify some things. So I get d prime times d prime to the power, and on top I have minus 1. And d prime times d prime to the power minus 1, that's of course 1. So 1 is at least 1, so indeed this constraint is satisfied. And so the smallest value for d to the power alpha satisfying the constraint is exactly d prime to the power 1 divided by d prime. Okay, now, so if I look at this function f of x, which is equal to x to the power 1 divided by x. So basically, what I have here is f of d prime. So that function has its maximum value when x is equal to e. And so this constant is of course 2.7 something. If we require that x is an integer, as in the degree of a vertex is always an integer, then the maximum value of f is when x is equal to 3. So we conclude that the smallest value for 2 to the power alpha that satisfies all of the constraints is 3 to the power 1/3. And therefore we can set L of n is equal to 3 to the power n thirds, and then all of these constraints are satisfied. So what have we done now? We have upper bounded the number of leaves in any search tree of the algorithm by 3 to the n third. And this is more or less 1.44 something to the power n. Now we have upper bounded the number of leaves, and it's very easy to observe that the depth of the search tree is also upper bounded by at most the number of vertices in G prime. Because every time we branch, we get rid of at least one vertex. So since the number of leaves is upper bounded by 3 to the n thirds, and the height is upper bounded by the number of vertices in G prime, we obtain that the algorithm has running time O star of 3 to the n thirds. So the other result that we get from this for free is that a graph on n vertices has order 3 to the n thirds maximal independent sets. Well, this is because, well, independent sets in this algorithm are only output at the leaves of the search tree, right? So that's the only part where something gets output and then there's no recursive call. So this is a leaf of the search tree, and we have upper bounded the number of leaves by 3 to the n thirds. So we conclude that, well, this is also an upper bound on the number of maximal independent sets, because our algorithm enumerates all maximal independent sets, and it cannot have more than this many leaves. In general, if you have an enumeration algorithm and your upper bound its running time, then, well, since it takes at least 1 unit of time to output something, you also have an immediate upper bound on the number of objects that it outputs. Okay, so this is for an upper bound on the running time, but how tight is this upper bound on the running time? Could we improve it just by refining the analysis a little bit? And it turns out that this is not the case, because there are actually graphs that have this many maximal independent sets. And therefore, since our algorithm needs to output each of these maximal independent sets, it cannot run faster than 3 to the n thirds. And so the graphs that meet this upper bound is a disjoint union of triangles. So what do we have here? So we have n third triangles. In our maximal independent set contains exactly one vertex from each of the triangles. And for each of the n-third triangles, we have three choices. So there's three choices which vertex from the triangle to include into the independent set. So since there's three choices and we have n-thirds triangles, we get 3 to the n-thirds maximal independent sets.